Greetings, this is TPU TV, I'm Ivan Ananin, and today we will talk about the latest innovations in the material development field and how they were inspired by carnivorous plant. Scientists have always been looking up to nature for the best designs, their recent obsession being the Venus flytrap, a true predator among plants. It can shut close in a tenth of a second once it senses its prey inside. To learn how it is possible, we contacted Dr. Juan Peralta from the Tomsk Polytechnic University, who has been working on a related project. Juan, please.
The mechanism of the plant is quite remarkable. Let me explain. First, the cells in the outer part of the leaf elongate. Then, when an insect falls into the trap, it stimulates hairs on the inside part of the plant. This triggers pumping of fluid to the outer cells, contracting them. Meanwhile, the inner surface of the plant doesn't change. This creates a mechanical force onto the leaves. But the leaves are built in such a way that they resist this force, creating tension. After nearly 1 second of build-up, the leaves can't resist no more. They become unstable and they buckle, flipping into a closed cup form.
This is a fascinating example of nature creating sophisticated systems through millennia of evolution, and mankind will definitely benefit if it learns from it. But how can we turn these concepts into usable materials? Let's hear what the experts have to say. Today here with us is Matvey Burlakov, the Materials Research Director.
Thank you, Juan. We as humans have always been learning from nature. Many different designs have been borrowed from living creatures. The Venus flytrap mechanism has inspired our scientists to create a new multi-layer material that would be able to change its shape in response to the outside stimulus.
To build snapping surfaces, a silicon polymer was molded into a flexible layer with circular indentations. This layer was then stretched and bonded to another layer of the same polymer over it, creating an array of enclosed pockets. When the double-layer material contracts, the second layer wrinkles to form a pattern of convex microlenses. Mechanical pressure can change the surface geometry within milliseconds. Chemicals, heat, light, or electricity can also trigger the snap instability, but the primary innovation is that there's a fast mechanical response without added energy. The key feature of snap instability is that there is a dramatic change in shape and geometry with minimal amount of pressure.
As one can imagine, the applications of shape-shifting materials are almost endless, from lifelike prosthetics that behave naturally to self-unfolding space structures and agile ocean exploration drones. We also believe that the production of such a material would be relatively easy, thus making it accessible to the small businesses and aspiring specialists.
Thank you both. I hope we hear more about those developments being implemented in the near future. And this is how a not-so-simple plant inspired the development of breakthrough materials, reported by TPU TV.